Dun, 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 dun. What's up, Asta? I'm currently the noms. What are you eating, Sensation? I had a protein shake just real quick. I have such a busy day today. It's crazy. Just non-stop, like, teaching and running around before I gotta fly for this wedding. What is this? This is Thursday, lecture 4. Cheese and chips and pizza, all the food groups, all the important ones. What's up, Sid? Okay. I'll start this soon. Nice, Aleph. Good. Glad you're able to do it. It's cool stuff, dude. I appreciate that you're learning more advanced physics things. Just, I can only help so much with that stuff. Especially at the end of the day when I've been, like, teaching for, like, 5-6 hours. I'm, like,
You done messed up, AA Ron!
I'm cashed. I'm like, I don't want to learn anything new. My brain is done. What am I doing? Oh, I'm loading Kudu. That's what I'm doing. Sorry. It took 1.5 hours? Wow. Well, I mean, congrats, dude. I'm glad you put the time in to learn it. That's awesome. I didn't have 1.5 hours on my stream to do it. I had like maybe 10 minutes. So that's why when I saw it, I was like, yep.
No.
Nope. That's not getting done. Maybe if it was like a slow day on a stream, I'd be cool to like spend like an hour and a half on a question, but otherwise, it's just not fair to everybody else who's asking questions for me to sink like half the stream into one obscure nightmare level wave equation. But I'm sure it was probably pretty cool. And it's a good exercise. You know, someone was asking about this actually on Campus Wire. They said, are there going to be derivations on our exam? And I said no. Right?
No.
I'm not going to make you do derivations on an exam. You can just copy paste it from somewhere, right? That doesn't. That's just annoying. It's not really teaching you anything there. But that being said, I don't want to discount the value in doing derivations. It is very important if you want to get a good overall understanding of how the underlying framework of our world functions. You know how physics is. Derivations are like one of the best ways to get an intuition, like get a feeling for that. And they take a lot of time and they're annoying and you can get stuck. I think someone also on Campus Wire was suggesting to use AI when you get stuck. And yes, that's a great use of AI. Yeah, definitely, I know a lot of people are worried in education because students are just using AI to just copy paste answers. But if you're using it to, figure out, hey, how did you get from this step to this step? Or can you explain the algebra here? AI is phenomenal at that. And I think that's an awesome learning tool that you guys have. You used to have to hire a tutor. I mean, you still can, but it's a lot cheaper to pay $20 a month to ChatGPT and have ChatGPT be like your tutor to figure out the in-between steps. So, yeah. Cool. All right, nice. Yes, today's lecture, we're going to go over a little bit more of capacitors, kind of like breaking down, simplifying circuits and then breaking them back apart. We're going to go over a little bit of dielectrics as well. Dielectrics are really cool, kind of a misunderstood thing in E&M. And then, reminder, we don't have lecture tomorrow at our regular time, but I will be doing an additional lecture tonight at, I want to say it's, 8 o'clock. Pacific. So, if you want to come by, and what I'm planning to do with that lecture is kind of some of the missed topics that we didn't get to cover in the last week or two. So that's going to be like dipoles, finding out electric potential for some kind of more interesting geometries, not the simple ones where it's like, oh, it's just an infinite line, or oh, it's just a sphere. And then also like charge on like shells and stuff. Yeah, AI is great for checking work. It's also cool for you to check AI.
Nice.
So like what I'll do sometimes is, I'll go through, and it's very interesting to notice when the AI screws up, and you're like, nope, that's wrong. And I love how AI is always like, oh, you're absolutely correct. Let me fix that. Is tonight the last lecture to be on the test? No. We definitely still got to put circuits on the test. I would say Monday or Tuesday is probably the last lecture that I'm going to put on the test, but it won't be heavily weighted towards Monday, Tuesday stuff. Yeah. We just got to... Hi, Reki. Yeah. So this is... This test is going to cover primarily Gauss's law, primarily electric fields, charges, potential, electric potential energy. And then I will have a couple questions that dive into circuits. We do have another exam before the final. It's next Friday. It's on the syllabus. I think I put everything on the syllabus ahead of time. I had some student last quarter who's like, oh, I didn't know we had an exam. I'm like, bro, what? Excuse me? It's been on the syllabus since day one. Although to be honest, Cameron, I didn't realize our next midterm was next Friday until I think Sib or someone brought it up. They're like, oh, what about next week's exam? I'm like, really? What next week's? Like, I haven't even gotten final grades for this week's done, or for the last midterm yet. Yeah, the summer's quick. The other teacher that does summer sessions, Nathan Tung, he's a great teacher, honestly, awesome guy. He does like 6 midterms during the summer, or like 5. He does a midterm like every week, which is nuts. So yeah, count your blessings. We only got 2 in the final. He does one like every week. Yeah. I've been scared since I saw it on the syllabus, JK. It's okay. Thanks for reminding me. Yeah, I guess I'm out with wedding stuff this weekend, so I'm pretty slammed. So when I get back Monday morning, I gotta like mad dash to make sure we get our next midterm drafted. It's a fast class. I enjoy teaching you guys. It's fun to teach. It's all the other administrative stuff that kind of gets to me, I wish I had I guess that's what my TA is for technically, but I don't want to put all that burden on Albert. He's such a nice guy, and I love Albert. And also, I believe he's a first-year graduate student, which means over the summer, he's studying for what's called the comp exam, which is a really, really hard exam that you take in between your first year and your second year of grad school, so like right before the second year starts. And it kind of determines whether you stay in grad school. Because if you fail it, you have to take it again next year, and it's kind of like a final exam of all the graduate classes you took your first year. So that's like classical mechanics, E&M, quantum, thermo, and it's a 2-day exam. It's, I want to say 4 or 5 hours per day. It's brutal, and it ends up like cutting out a decent percentage of the graduate students. So you really have to lock in and like study all summer for that exam. And so I don't want to take that away from Albert. I want him to be able to spend some time studying for that because it's important. I luckily didn't have to TA the summer before my comp exam because I had a research grant, and I just ended up living at my lab for a month. I literally packed a suitcase and I just slept at my lab for a month, and every morning I would just wake up, go through practice exams, repeat, just like kept doing that. And I barely passed. So, but I'm here. I'm still here. Okay, cool. All right. Let's start lecture off. Again, if you have any questions and stuff, dump them in the chat. All right, week 4, lecture 4. Yeah, today we're going to go over a little bit more of capacitors. We're going to say like more complicated capacitor situations, right? Okay. So some key things we learned about how capacitors can be arranged in electric circuits, right? Had to do with whether things were in what we call series, right? So for instance, these are series capacitors. And we learned that, right? Let's say this is like C1 and C2. We learned that C total was equal to 1 over C1 plus 1 over C2 all to the negative 1. And then we also had capacitors in parallel. So you could have had something like this. There we go. My art is great today. Okay. These are parallel capacitors. And then in this case, C total is equal to C1 plus C2. This will be the opposite for when we do resistors next week. But for now, yeah, capacitors. It's just how the class is structured. They want us to go. I find it useful to do capacitors after you've learned how to calculate electric field and potential, because that's really what capacitors are. They store potential and cool stuff. But then we like dive into like, oh, but we also need to get our feet wet with how circuit diagrams work. Okay, there's some other cool properties about capacitors being in series and being in parallel. When capacitors are in series, okay, they have the same charge. Each capacitor has the same charge on it. So we would say like capacitors have the same charge. Okay. And let's remember like properties of capacitors. We learned this, right? Q equals VC, right? So this is charge, this is voltage, this is capacitance, okay? So series and capacitors have the same charge on each one. So I could say like Q1 equals Q2. However, they have different voltages. So same charge, but different. And we can say like distribute voltage. So for instance, V1 does not equal V2. All right. For parallel capacitors, okay, these have the same voltage. So we say capacitors. And so that's V1 equals V2, but then they have different, and we're going to say like distributes charge. So Q1 does not equal Q2. Okay. That's the important properties of capacitors in series and parallel that we want to learn. And then we can use that to diagnose in circuits a bunch of cool things about different capacitors. Oh, I should label these. Let me label this. C1, C2. Do we need to understand the intuition for this or understand it's true? I would say both. And we are going to do the intuition. I'm going to show some diagrams of the intuition. Let me do like some practical examples with like clicker questions first. And then we're going to go through like some diagrams to be intuitively like, you know, why is this? Why is the charge the same on one, but why is the voltage the same on the other? Yeah. No, that's, I like a little bit of balancing. I say like when you're learning things, you have to balance like three things. It's like procedural fluency, which is the ability to like do problems. And then there's like conceptual understanding, and that's like understanding, okay, why does the math work? So procedural is like, can I do the math? Conceptual is like, why is the math? And then the third thing is like applying it to other situations. So they call that like the application phase of learning. I tend to like to teach where we do procedural first to get like some wins, right? If most people can do math, I hope, right? So if we teach you, and then also most students, when they look for help or they look for instruction, the first thing that's on their mind is, can I do the problems? Can I get questions correct? And so to set that up, to get students like a little win, I make sure that we understand procedurally, how do I do it? Okay. And then once you have the confidence of like, I can do the math, this isn't tough, like this isn't scary. How do I understand conceptually why that is? And that builds like a more like, you know, holistic understanding of the physics and what's going on. And then the third step is if you really got them hooked, right? And they're like, oh, I actually love capacitors, really fucking cool. Then you'll start asking, how does this apply to other situations? Like, what would happen if I did this? Or, how do we use this in real life? Capacitors get used for a ton of things. Just like quick little side tangent. They get used as filters. So a lot of times to filter out different frequencies in signals. They also get used as like temporary batteries. If any of you guys end up owning a Lamborghini at some point, the new Lamborghini, which I think is the Temerario, uses what's called like a super capacitor. And basically what it is it's a battery that's able to discharge its power extremely quickly. Capacitors can discharge electricity and power a lot quicker than a battery can. And so they can't store a lot of energy. That's what a battery is for. A battery can store large amounts of energy. A capacitor can only store a certain amount of energy, right? Due to that 1/2 CV squared. But the advantage of a capacitor is it's very quick. You can get energy in and out of a capacitor much faster than you can with a battery. So some practical applications of capacitors. All right, let's see. Let me pull up one of the clicker questions we got. Once I get my Lamborghini check-in, thank you. Yeah, please do. It is a real thing. I just find it funny that they market it as like super capacitor. I'm like, okay. It's like the flux capacitor in Back to the Future. Yeah. They call them here, this is if you guys want like to see a little web thing. What are super capacitors? Oh, this is a 5-year-old thing, yeah. It's funny. So it's not a very powerful engine. It's only a 34 horsepower engine. It's very, very low compared to the 800 horsepower the gas engine makes. But they talk about the capacitors here. This is really cool. Yeah, it's because capacitors just discharge energy like really quickly. You can dump stuff really quickly. So it's able to like dump that extra 34 horsepower like super fast. But that car is also $3.6 million. Not today, unfortunately. I don't think I'm buying it on this salary. Okay, let me. Ooh, I need to make this. I thought I set this chapter to be live. Come on. Come on. Lecture 16. Visible. Make it visible now. Make the due date later. PM. Cool. All right, so let's go back. Refresh. There we go. Lecture 16. Cool. All right. Says 4 identical 13.4 nanofarad capacitors are connected in parallel to a V0 equals 12 volts potential source as shown in the figure below. Find the charge stored on the capacitor that is furthest away from the potential source circled, whatever, figured below. All right, let's paste it in. Get you guys the clicker answers. Nope. Okay, cool. So everything here is in parallel, okay? And what we said about things in parallel, right? Parallel has the same voltage. Okay? So whatever is lined up in parallel with this source will also have the same voltage as this source. Do you see how everything here is like literally up down parallel? You could also redraw this if you wanted to, right? You could redraw it with all of these. So let me make sure I draw some things here. For a battery, this is a battery. we talked about, right? The longer line is the positive side because it takes more ink to draw a positive side. This is negative. So that means on all the capacitors here, right, this positive charge is going to flow like this. So you're going to have positive charge, positive charge, positive charge, positive charge. And the negative charge here is going to flow this way. And it's going to deposit here. Negative charge, negative charge, negative charge, negative charge. Okay? Something you should notice, right, is that all of the negative charge ends of my capacitors here are technically all connecting to the same point. They're all connecting to the negative end of the battery. So what I could do if I wanted to draw this, right, I could just have, let's have this be the negative end of the battery, right? And we could have just done this. And this is something you'll get good at just with circuits, is being able to like kind of reimagine how things are. And then the positive ends of all these capacitors are attached to the same positive end here, right? So now I can just do this. And sometimes this kind of helps students to see. They're like, oh yeah, look, all of these capacitors are in parallel with each other because all the negative ends of the capacitors line up with each other and all the positive ends of the capacitors connect to the same common point here. Okay. If we wanted to, for instance, figure out, I'm going to do kind of the long way. There's a very short way to just solve this in like 2 seconds, but I want to like build a little bit of intuition here. If we were to figure out, let's say, for instance, what the total capacitance of this thing is, right? This would be C1234, right? We want to like kind of make this as like just a single capacitor. We remember that since the capacitor is in parallel, that adding up the total capacitance is just adding them, you know, linearly like this. So this would be equal to C1 plus C2 plus C3 plus C4, right? And we said that all the capacitors were identical, so they all have the same capacitance. So let's just call that this capacitance here. Let's just call this like, for instance, like C. Or let's call it like C naught. Then C1, 2, 3, 4 is going to be equal to 4 C naught. Okay? So now you could have an equivalent circuit here that just has a single capacitor. C1, 2, 3, 4, which is equal to 4 C naught, right? And if this is a 12-volt source, right, by what we're going to learn later with loop laws, but this also is just going to be at 12 volts, right? So this whole thing here has a voltage equal to 12 volts. We could also calculate the charge. Let's calculate what the total charge would be on this super resistor, right? If I wanted to do that, right, I know Q is equal to VC, right? So I'd say Q1234 is equal to the voltage on this supercapacitor, which this is 12 volts, because that voltage is being provided by this battery, right? This capacitor is the only thing connected to the battery, so the capacitor will have the same voltage as the battery. And then this would end up being 4 C naught, right? So then if we wanted to get some numbers here, right? So this is going to be 12 times 4 times 13.4 times 10 to the minus 9. Cool. Okay. So Q1, 2, 3, 4. And then here, let's get a number for that. Calculator. There we go. I'll show you why I'm calculating the charge here in a sec. It's to show something cool. Okay, so that tells me that Q is equal to 6.4 times 10 to the minus 7 coulombs. Okay, so that's the charge on the whole thing. All right, now going back to our circuit as it was, like with the individual parts, not with the supercapacitor. We know that capacitors in parallel have the same voltage. So this voltage is the same as what the voltage of the supercapacitor was. So these are also going to have 12 volts on them. So this one right here, the one we're looking at, this is going to have 12 volts on it. And if we want to figure out the charge that's stored, right, that's Q. Well, then Q4 is going to equal to V4, which is 12 volts, times C, times the capacitance. So that's going to be 13.4 times 10 to the minus 9, right? Do a little math there. So 12 times 13.4 e to the negative 9. And that gets me 1.6 times 10 to the minus 7. So nanocoulombs is 10 to the minus 9. So divide that by 1 e to the negative 9. And there you go. So you get 160 nanocoulombs. Or 161, basically. It rounds up to 1. Yeah, 161. Fine. Okay. So that correct answer choice was A. Now, I want to show you something cool here, right? So since all of these capacitors, right, have the same voltage, and they all have the same capacitance, right? That means I have 161 nanocoulombs here, 161 nanocoulombs here, 161 nanocoulombs here, and 161 nanocoulombs here. If I wanted to figure out the total charge amongst all these capacitors that's being held, right? I would just add 161 plus 161 plus 160, so it's just times 4, right? Notice that gets me 643.2 nanocoulombs. So if we do 643.2 times 1e to the negative 9, that gets us our same answer from before, 6.4 times 10 to the minus 7. So there's a really cool thing here, which is that while every capacitor has the same voltage, right, as the supercapacitor that I build when I condense it, the charge on each one will add up to the total charge on the supercapacitor. And it turns out, if these capacitances are different, the charge will distribute proportionally. So if something has more capacitance, it'll take up more of the charge. If something has less capacitance, it'll take up less of the charge. But that kind of goes into here when we say, when I said distributes here, it distributes proportional. Well, in this case, charges distributes proportional to the capacitance. So we'd say more C. So we'd say capacitors with more C have a greater share of the Q. Okay? And that comes from that's from the math. We'll go over the intuition of this later. But okay, cool. So if we go answer that should have been answer choice A, not B. Why is it automatically selecting answers? That's whack. Does it say saved though? Oh no, okay, we have this. Oh, it does say saved. Interesting. Oh, but it didn't submit one for that one. Okay, whatever. All right, cool. Saved. Answer choice A. Cool. Okay, nice. That's a pretty chill one. Let's go to question 3. Now we're going to deal with things in series. Okay. And now the capacitances aren't the same. So it's not as easy. We're going to question 3. I'm going to skip 2 because I want to come to that later after we've done series and parallel. Okay. Question 3. Imagine a dimension where instead of space there is matter. Now you understand why I'm mad. What? What? There's dark matter, there's all sorts of stuff. Okay. All right. They want to say calculate the voltage across capacitor 2. And they say 3 different capacitors are connected in series with a V0. They should have drawn something here. They didn't draw the battery. That's lazy. They should have drawn this. Okay. This should have been V0 is equal to 1 volt. Okay. And if this is the positive end and this is the negative end, right? That means positive charge is going to move to charge this end of the capacitor positive and the negative end of the capacitor here. And then if we look at what the charges are for everything in between, right? This is positive, this is negative, this is positive, this is negative, this is positive. So notice, when the capacitors are connected, so it's negative to positive, that's something in series. Versus in parallel, all of the positives connect to a single point, all the negatives connect to a single point. I'm reiterating this a lot because it's going to come up a lot when we start doing resistors. And so I really want to make sure you understand the intuition here. Okay. So I know things in series, right, have different voltages, but they have the same charge. Okay. But I don't know how much charge is on each capacitor here. So my solution, or the way to my solution, is to take all of these and build a supercapacitor C123. Now, what we have to remember is that for capacitors in series, this is equal to 1 over C1 plus 1 over C2 plus 1 over C3 all to the negative 1. Okay? So, let's pull out our calculator, throw some values in. Okay, so 1 over 195 e to the negative 9 plus 1 divided by 204 e to the negative 9 plus 1 over 283 e to the negative 9. Really, really big number. But then I'm going to raise this to the negative 1 power. Cool. So there's my overall capacitance. So I get that. And here, let's divide that by 1 e to the negative 9 because I want to show you like what happens to the capacitance. So, so now you have an overall capacitance of 73. Right? So now I say, okay, well, capacitance C123 is equal to 73.7 nanofarads. All right. Cool. The next thing we want to do, right, is we want to calculate what the charge would be on this supercapacitor. I already know what the voltage would be, right? This supercapacitor is the only thing connected to a 1 volt voltage source. So I know that V123 is equal to 1 volt. And now I'm going to use Q equals VC to solve for the total charge on my supercapacitor, which again would look like this. Yeah. All right. Oh, well, it's just times 1. Oh, ha. Okay, cool. So you just multiply by 1. So that's 73.7 nanocoulombs. Awesome. Okay. Now, what I know for capacitors in series is that they have the same charge, okay? So whatever the charge is of the big thing, that's the same charge of each little individual component. So I know that Q2, which equals Q1, which equals Q3, is equal to 73.7 nanocoulombs. And so now if I want to figure out V2, okay, that's just going to be Q2 over C2. So that's going to be 73.7 nanocoulombs divided by 204 nanofarads. So the nice thing here is we're using nano on both, so I don't need to write the times 10 to the minus 9, 10 times 10 to the minus 9. I can just cancel it. So I'm going to do that divided by 204. And that's going to get me 0.361 volts. Now, just for to show a point here, let's figure out what like V1 would be, right? V1 would be Q1 over C1. So that's, again, 73.7 nanocoulombs, because every capacitor has the same charge in series, divided by 195 nanofarads. And then V3 would be equal to Q3 over C3. And C3 is going to be 283. Would there be a way to do this without the supercapacitor? I don't think so. I think you have to create the supercapacitor to figure out the total charge. And then Yeah, watch this, Sophia. You're gonna see it. I'll show it to you. This is a cool thing. So here, let's calculate these. So for V1, that's 73.7 divided by 195. So that's going to be 0.378. And then this is 73.7 divided by 283, which is going to be 0.26. And here's a really cool thing. I think this is super, super awesome. If you add up all the voltages from each individual capacitor, look what you get. So if we add these all up, let's make like a bigger. You end up getting 1 volt total. So watch that plus that plus that 0.99999. Yeah, it's basically the same thing, right? So this ends up equaling 1 volt total. So here's the cool thing, right? So for capacitors in series, the charges are all the same as the supercapacitor. The voltages are different, but the sum of all these voltages has to equal the voltage across the whole thing. As opposed to with parallel, right? The voltages are the same, but the charge has to add up to the total charge. And here you can see it's inversely proportional, right? The more capacitance you have, the less voltage you take up. Okay. So, I mean, the answer to this one, because we wanted the voltage across the second one, that's just 0.361, right? Also answer choice A. But let's amend our notes here, right? So we would say, let me make the same thickness. Capacitors with more C have a lower or lesser share of the voltage, right? So Sophia said total charge. Yeah, so in series, the total charge on this big capacitor is the same as the charge on each individual capacitor. And we'll go into the intuition of that in a bit. The voltages add up to the total voltage. In parallel, the voltages are all the same, and the charge adds up to the total charge. There's a key difference between these two. It's kind of cool. There's like a yin and yang to it, right? This is where, I don't know, I start thinking this is like really cool, that physics has these like symmetries, right? You have things that like, oh, if I flip this, this flips. And it seems kind of not connected to each other, right? You're like, wait, why does the math then flip this thing? Like, what's the physical reason why that happens? Thanks, Sensation. Okay. So the answer for that one was A for question 3. So let's choose A. Cool. Nice. Okay. Let's do this third question, because this will be like going from series to then going to parallel. Let's see if I get this one right. This one looks kind of tricky. I'll try to explain it the best I can. This is question 2. Damn, this guy just aura farming 24/7. Appreciate it, H. Yeah, we're going over physics. We're doing capacitors. You want me to do what? Is it the Thai boy, the Thai boat boy dance or something? What does he do? He does this or something. That kid's life changed like overnight. That's pretty crazy. Just the internet decided, just like, you, bro. I think he's now the ambassador for Indonesia or something. Like the ambassador for, I don't know, like tourism or something. They gave him like a celebratory position. Okay. Answer choices. Okay, it says two capacitors are initially connected in series with a voltage of 0.725 kilovolts, and it's applied across the combined capacitors as shown. Capacitor A has a capacitance of 2 microfarads. Capacitor B has a capacitance of 4 microfarads. The charged capacitors are then disconnected from the voltage source as well from each other. Finally, the two capacitors are connected to each other in parallel so that their positively charged sides are connected together with a wire, and their negatively charged sides are connected together by another wire. Okay. Find the final voltage across each capacitor. Interesting. Okay. All right. So let's maybe like solve for some things here first. So when these things are connected to a voltage source, right, and they are in series, we know they're going to have the same charge. So let's figure out like what the equivalent capacitance would be here. Let's break this into our supercapacitor. Not the Lamborghini supercapacitor, but okay. CAB, right? We know is going to be 1 over CA plus 1 over CB to the negative 1. So let's get a capacitance for that. Okay, that's going to be 1 over 2e to the minus 6 plus 1 over 4 e to the minus 6. Okay, and then we're going to raise it to the negative 1 power. And so now we have, and let me divide this by e to the minus 6. It's just 1.3, right? Yeah, cool. So we have 1.33 microfarads. So CAB is now equal to 1.33 microfarads. Okay, that's the combined capacitance. So if I draw my diagram now, right? This will be CAB. This is V naught. So we can calculate what QAB will be, right? Because I know things in series have the same charge, right? So let's calculate QAB. So that's equal to VAB times CAB. And so was the voltage just 1 volt? No, it's in kilovolts. Ew. I thought they were making life nice for us. Okay, times 0.725 e to the 3, so basically 725. Okay. So we end up getting, and then that's times 10 to the minus 6. Because I have microfarads. Okay. So now we have 9.67 times 10 to the minus 4 coulombs. And that's going to be on this one, and it's also going to be on this one, okay? So let's see, 9.6 times 10 to the minus 9.67 times 10 to the minus 4. Okay, cool. All right. Then we take them apart, right? We tear them apart. Okay. So we're removing this, right? We cut this off. So now the positive charges can't really go anywhere. We also cut this off. So the negative charges can't go anywhere. And we cut this off so they can't like redistribute. We do this all at the same time. We cut everything off at the same time. Doing that, right? Now, this thing still has 9.67 times 10 to the minus 4 coulombs on it. This still has 9.67 times 10 to the minus 4 coulombs on it. And now we're going to connect them together so that these positive plates are now going to become... This right here looks the same thing as one big massive plate. So these are in parallel with each other, right? But now you have one big plate, and each of them had 9.67 times 10 to the minus 4 coulombs. So the new charge on our parallel capacitors here is going to be, let's call this like, let's make this a, let's turn this into just a single CAB, right? And that's going to equal to CA plus CB, because they're in parallel. So what's that? That's going to be 6 times 10 to the minus 6 microfarads. Okay. But now the charge, right, across this supercapacitor is the sum of the two charges that were on these capacitors when they were still connected up to the battery. And so we can say that QAB is going to equal to QA plus QB. And so that's going to be 9.67 times 2. So we're going to say 2 times 9.67 times 10 to the minus 4 coulombs. Okay. And now since things are in parallel, right, now that we've connected them in parallel, we know that VAB must equal VA must equal VB. Right? Whatever the voltage is on one leg has to be the same as the voltage on the other leg, has to be the same on the voltage of the whole thing. So we can use our information here to figure out this. So Q over C is equal to V. We can say like QAB, CAB is equal to VAB, and that's also going to be equal the individual voltages. And so that gets us 2 times 9.67 times 10 to the minus 4 coulombs divided by 6 times 10 to the minus 6 farads. Okay? Which, if we pull our calculator out, so 2 times this answer, and then divide it by the new capacitance, which is 6e to the minus 6. Now we get 322 volts, which is the same thing as VA, which is the same thing as VB. So the answer should be answer choice E here. Okay. I think that's correct. Let's go check it. E. Magic. Yes, nice. Okay, cool. We got that one right. Nice. Right, okay. So VA equals VB is for parallel circuits, and in this situation, they are in parallel. Because notice how the positive end and the positive end connect to each other, right? You could imagine there's like some imaginary line here. And then the negative end and the negative end still connect to each other, right? And this is the negative. What happened is we like physically modified the circuit. So we started out with V0, right, running through these resistors, and these resistors were in series. You are totally correct that the voltage here would be different than the voltage here while it's connected to a voltage source. However, how capacitors work is when they're connected to batteries, batteries like slowly dump or like rapidly dump electrons or anti-electrons, like they pull electrons off to create positive charge. But they dump charge on each end of the capacitor is what they do. Okay. And in doing so, okay, now you build up charge on each capacitor. But for capacitors in series, the charge needs to be the same, right? So that's why these things. So in a series, one capacitor is affecting the other, preventing more charge from flowing through, so there would be total less capacitance. Yes, and you should have seen that, right? So here, right, you had a 2 farad and a 4 farad, but combined it acts as an effective 1.3 farad or microfarad, sorry. So, yeah, you get overall less capacitance. Yeah. That's a good way to think about it, Sib. So these have the same charge, and then we disconnect them. We disconnect everything from itself, right? The charge can't go anywhere, right? This 9.6 times 10 to the minus 4 charge I have on CA can't go anywhere. So it's going to remain on capacitor A, and this will also remain on capacitor B. Now, when I connect them such that the positive end and the positive end are next to each other, those charges are going to combine. If I connected these like positive to negative, these would discharge. Right? So when the charge is the same for all of them, the total charge equals the same charge. But when it's not the same, the total charge is the addition of them. In parallel, yes. In series, no, it does not matter what the capacitance is. In series, they will always have the same charge as the combined supercapacitor, the big one. In parallel, things have the same voltage, but their charges add. Yes, exactly. Well, no. VA equals VB in parallel. Right? So when they're in parallel, these things have the same voltage on them. Which is why we wrote this, right? So if I find the voltage of the equivalent capacitance, or the supercapacitor, which is CAB, then that voltage is also the same on each one of these things. You're good, Amelia. Yeah. Yeah, it's kind of tricky. There's a lot of little different concepts to this. We are going to do Kirchhoff's. Yes, we are going to do Kirchhoff's law next week. It's really cool. We're going to do the loop law. We're going to do the juncture law. We're going to do some interesting examples of that. Okay, let's try to like explain like why this is and stuff. Okay, let me see. Capacitors. I want like a nice picture. No, that sucks. Man, they don't have any nice pictures in this textbook with how like series and parallel works. Fine, I'll go find it myself. Make shit up. I don't care. Don't say Kirchhoff. What's wrong with Kirchhoff? Kirchhoff? You want me to say Kirchhoff? One sec. Parallel. How do you Smirnoff? Yeah, here we go. This is what I wanted. This is what I want to kind of show. Wow. Oh, they actually have some really cool pictures of these. I like these. One sec. Let me pull these. These are some great diagrams. I should tell the textbook people, y'all need to steal these. And then let me get the series one. Correct. Yes. Yes, and I'll show you why they're equipotential. I want a diagram. Doing it in series is a little bit trickier. I feel like I can get it though. Let me see. Sensation's going off on my my English pronunciations. Okay, here. All right, let's look. Okay, so for instance, these are capacitors in parallel. All right, parallel. So if you had like the positive end of the battery connected to all the same points here. Oh, sensation, be nice. And the negative end all connected here, right? This is the same thing as connecting all of these plates together to make like a super plate. I know you do, sensation. I appreciate it. And in that case, this super plate would have the sum of all these negative charges together on it, right? And so that's why the charges add up to like the super capacitor charge. You can think of all these plates like because look, they are connected by a wire. Anything that's connected by a wire, you can literally connect to each other, right? Wire is assumed to have like zero resistance and just directly connects things. So instead of thinking of like this part of the plate being so far away, you could think about it just being like literally right here. And then just connecting this wire here right up to here. And then these two wires provide the same thing. You're not going to have different currents going through the same like juncture of wire. So this is why parallel capacitors in parallel, the charges will add up. And then the voltage, the potential difference across each one has to be the same, right? Because you're looking at the voltage across like this whole thing, right? What could create any sort of like different voltage? I mean, there can't, because all of these things are being held at the same potential, the same equipotential, and all these top plates are being held at the same potential. So the voltage across each capacitor has to be the same as the supercapacitor, but the charges do not, right? The charges have to add up to what the total charge would be for the supercapacitor. Okay, in series, it's a little trickier. I'm trying to think physically how this works. I agree that minus charge builds up here, positive charge builds up there. Okay, I think I see something here. This is something cool here, actually, right? So if you start building up positive charge here, right? Equivalently, right? That's going to start sucking whatever electricity it can, whatever electrons are available to start moving towards this plate. But nothing can actually jump the gap, right? So what you end up having, right? Because these, you can think about these pieces right here just being like gone, right? Because they're not connected to the battery. The battery only connects to the bottom of this plate, the negative end, and the top, the positive end of this plate. So the only plates that you're actually like moving charge is going to be here and here. Oh, there's lag? Uh-oh. Let me make sure my chat's keeping up. Sorry. Where is my chat? Oh, there it is. Okay. Yeah. So in order to create positive charge here by like kind of like charging by induction, right? You're going to influence whatever neutral charges are here to pull the negative ends over here and the positive ends here. But the overall charge, right, amongst here has to be 0. Do you see here how, for instance, like minus Q Or here, we could say this is like, let's call this like top, bottom, top, bottom. Okay? So if the top has a positive Q charge on it, okay, that means it's going to influence the bottom here, right, to have a negative Q charge, right? So we could say like Q bottom is equal to negative Q. And if this thing was neutral, right, because this is not connected to the circuit, right? It's just two plates connected to each other. They're in like the nothingness of vacuum, right? This thing started out as neutral. So Q bottom 1 plus Q top 2, right? The top of the second plate. This has to add up to 0. And if this bottom plate is negative, in order for the overall charge here to be neutral, to be 0, this thing is going to have a positive charge Q. But if this has a positive charge Q, then this is going to influence this to have a minus charge Q, which again will influence this to have a positive charge Q, and this one will have a minus charge Q, which will make sense because that minus Q is coming from the negative end of the battery here. So the charge on each capacitor is all going to be the same. They have the same charge. And it's because you can kind of think of, well, this whole thing just like kind of goes away to 0, right? Now, what can change though is the potential, right? Because depending on the capacitance, right? If this is the same everywhere, right? Then changing capacitance means you do have to have a change of potential. And that has to do with, for instance, like how big these gaps are, right? Even if these have the same charge on each plate, let's say this one is like further apart from this one. In that case, you would have a lower electric field, right? And a lower electric field means you would have less potential difference between the two. So, yeah, this is why all the Qs are the same, but the voltages, they eventually you have to get the same voltage difference from here to here that you would with the battery. So all the individual voltage differences between here and here and here have to add up. And this is something we'll do when we do Kirchhoff's law. We'll talk about like adding voltages in series and like doing loops and things. Yeah. Okay. Does that make sense? Or is my YouTube really, really lagging? I don't see any frame drops. Looks like we're doing okay on the network. Let me know, chat. Say thumbs up. Yes or no. Make sure I'm not just speaking into the nothingness of the ether. Yes, cool. Awesome. Awesome, good. Okay, cool. Okay. So good. Okay, cool. And yeah, keep in mind, whenever we're doing like Q equals VC, this is always referring to the positive charge on one plate. The bomb has been planted. Yeah, sensation. No, I was just making sure that YouTube wasn't lagging crazy. So the net charge on a capacitor is always 0, right? Because the positive plate and the negative plate they have to be equal and opposite. However, whenever we do our math with this, Q equals VC, or I don't know, whatever the other stuff, we're always referring to the Q as like, what is the positive charge on one of the plates? You can't have different charges on different plates. You can't have different charges on different sides of the same capacitor plate. That just doesn't happen. Okay. Cool. All right, let's see if I got a little bit of time for dielectrics. Yeah, we got 10 minutes? Okay. We're not going to do any questions on dielectrics, but I think you have stuff in the homework. All your base should be taught to all people as a matter of necessary history. All your base belong to us, sensation? Is that the next thing we're saying? Okay, let me pull up some of the dielectrics, because dielectrics are cool. They are commonly misunderstood, but and it has to do with what you see, that epsilon naught thing we have and whatnot. Sorry. We get signal. Okay, so for everything we've been doing so far, we've assumed that the space in between the capacitor plates is vacuum, right? Or free space, right? So far, nothing in between the plates of a capacitor. However, if you were to insert something like a material, okay? So if you were to insert a material in between the two plates, so if you have a new material in between the plates, this ends up increasing the capacitance, where we would say like C nu is equal to kappa C0. And this is the original, okay? And the reason why that is that this dielectric here decreases the potential in between the two plates, because it's like something that's like getting in the way. Say, because V is now equal to 1 over kappa V naught, all right? And so this is, you look this up on a table for different materials. Okay, if we want to understand like why that is, okay, so for instance, like, wait a minute, why does inserting something here start dropping my potential between the two plates? We can start thinking about the molecular form of what a dielectric looks like. Let me get a cool little graph of it. Yeah, okay, cool. So we got to talk a little bit about polarization. I didn't do dipoles yet. I think I will maybe cover some dipoles tonight, because dipole moment is kind of important. And this is also like an allusion to chemistry. So you know that atoms, right, can, or maybe you don't, but if you've taken chemistry, you've learned the difference between like polar molecules and nonpolar molecules, right? So for instance, CH4, right? That's I think that's a nonpolar element, right? Methane. And the reason for that is you have carbon here, and you have like hydrogen, 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 and they all pull in equal spaces. So the individual positive charges, and whatever the negative charge here, they balance out, right? Okay. But you can also get polar elements. So for instance, like H2O is definitely polar. Because if you have oxygen like this, right? Positive, minus, now you get electric fields that don't cancel each other out, okay? So when things are polarized, they have what's called like, right? They have a positive end to themselves and a negative end to themselves. And if they're seen in the presence of an external electric field or like external charges, they will align their dipole moments up to whatever their environment is. So for instance, if something is polarized, right, with a positive end here and a minus end here, then if you have an electric field, right, that's going this way from positive to negative, it will align itself such that the positive end of the molecule starts moving in the direction down with the field, and the negative end gets closer to where like the field is starting. So if you have like positive charge and negative charge here creating an E field, then the dipole moment tries to like kind of line up with it. I think, does dipole moment, does it point from minus to plus? Yes, in physics, dipole moment points from minus to plus. I'll go over this a little bit more in tonight's lecture. But this, for instance, is the dipole moment. And then this right here would be, for instance, the electric field that it's in. We say like electric field, E. Okay. And polarized molecules will attempt to line themselves up such that they're in favorable positions for the electric field. You can also have things that are unpolarized, okay? So, for instance, like we said here, and if they get put next to something with a strong enough electric field or a strong enough electric charge, they get what's called like an induced dipole moment, which I think this is what van der Waals forces are, or like London dispersion. Correct me if I'm wrong. I don't remember all my chemistry, but so things don't have to be polarized in order to be affected by external electric fields. You can actually like create dipole moments as well. Now, let's say in the case of our capacitor, okay, which we're going to say here, right? Let's say this was our capacitor. And let's say it originally had some sort of electric field pointing across it, right? Because let's say there were positive charges on this end, there were minus charges on this end, and then that was hooked up, right, to a battery, which was providing that positive and minus charges. Okay. If instead of having nothing in between these plates, if instead we have a material, and let's say this is called a dielectric, it's a dielectric material. Let's say this material is polarized, right? Or not is polarized, sorry, is polar. Okay. Then you can think about it having all these random positive and negative ends of itself just like kind of floating around and stuff. Or they're really in place, but they can rotate. Now, if you put this in the presence of a capacitor, okay, where now we have positive charges on here, we have minus charges on here, okay, and you have an electric field being created because you have a battery hooked up to this capacitor. Now, the individual particles in your dielectric, in this thing in the middle of the capacitor, they will line up with the electric field, okay? And in doing so, they now create like a back electric field, or what we call this is like EI. This is induced E field. Because look what happens, right? If the things line up, now I have positive and negative ends to my individual, atoms in my dielectric. That creates its own induced electric field that points in the opposite direction as the electric field that's being created by the battery the capacitor is hooked up to. And in doing so, now your total electric field is equal to E0, right, plus E induced, but this is negative because it points in the opposite direction of your original electric field. And in doing so, you weaken because let's remember also electric field and potential, right? V over D is equal to E. So if you decrease the electric field present between these two plates, you're also going to decrease the potential between these two plates. And then, right, Q equals VC, or Q over V is equal to C, I guess, yeah. So you start dropping the voltage and dropping. So if you're dividing by a small number, now this starts going up. So if now your voltage is 1 over K V, because remember from above here, oh, we did it here, sorry, right? So voltage, right, is now 1 over K V naught, because this shows us that the potential is dropping due to something else being inside the two capacitors. Now your new capacitance is K Q over V. So that implies that C is equal to K C naught. Right? This is where this comes from. So, yeah, dielectrics are cool. They're a way to raise the capacitance in an object. And this is why, for instance, you can get really cool things. So if you want super high capacitors, if you work in any sort of like high energy physics lab, you'll see things called capacitor banks. And this is what they use to dump like insane amount of power into like lasers and like these things. They're huge. Yeah, I've worked with these before. These are oil capacitor banks. So these have plates in between them. But in between the plates holding these charges, they have oil, which raises the amount of capacitance that's possible for these capacitors. The reason why you want to raise the capacitance is there's eventually what's called like dielectric breakdown, which is if you put too much voltage across a capacitor, right? If I put like way too big of a positive charge and way too big of a negative charge here, you will actually break down the dielectric, and the dielectric will now allow electrons to like move across. And that's called dielectric breakdown. That's when capacitors like arc, and that's when things explode and a bunch of bad stuff happens. So we have come up as engineers with cool ways to really increase the capacitance by using unique dielectrics that kind of like allow the tension in a capacitor to get bigger and bigger, so that we can do super cool science stuff. Okay, cool. I hope that made some sense to you guys. Sorry, we went a little bit over time, but I like to like connect things to the real world. Be like, this is why capacitors are used, not just because of Lamborghinis and things. Cool. Okay. We do not have lecture tomorrow. I'll repeat it again. No lecture tomorrow. There is a lecture later tonight at 8 p.m. So come on by if you can. If you can't, don't worry. The lecture will be recorded, and I will give you through the weekend to do next lecture's clicker questions. You still have to do these clicker questions by tonight, but for the makeup lecture I'm doing later this evening, those will not be due until Monday. Okay? All right, cool. Enjoy. I'll see you later today. If I don't, enjoy the weekend, and I'll see you on Monday. Cool.